Maybe I'm too stupid for this.
Well, we're live, yeah, we're live.
So therefore, excuse me, I don't think I have COVID-19, but I do have a sinus problem. So we'll try to take care of that with sips of water from time to time. So most visible sunlight wavelengths come through the atmosphere, but the greenhouse gases, the carbon dioxide and a number of others, methane in particular, natural gas, they reflect the emitted wavelengths in the infrared region back to the surface of the Earth. So they can't get away. So the Earth stores up more heat than it's used to storing up, the more greenhouse gases that are up there to cause greater reflection of the Earth's attempt to reduce its temperature. They send it all right back and say, tough luck, try again. So concentration of greenhouse gas is what makes the difference. And so bottom line is if we don't, the temperature of the Earth, simple, straightforward physics, has to go up in order to get rid of the excess heat that's taken on during the day. Let's look at some spectra here. This is the Planck's black body radiation spectrum, and the sun spectrum looks like this. Notice that that's a log-log scale, by the way. Logarithmic vertical axis, logarithmic horizontal axis. But you can see that the sunlight peaks in the visible range, and the Earth's radiation is way out in the infrared range, and in fact, there is no visible radiation leaving the Earth. It's just plain infrared, and you can see that it is something like 10 to the 5 times 10 to the 7 watts per square meter per meter of wavelength versus 10 to the 14, so it's almost 7 orders of magnitude less than the sun's radiation. Now, you gotta be a little careful about how you interpret this, because the sun is, remember, it's 93 million miles away, so by the time it gets to the top of the Earth, the intensity is down to 1,367 watts per square meter and 1,000 watts per square meter as it gets down to the surface of the Earth. So, but anyway, these are the radiation curves, and it turns out that these carbon dioxide lines and the greenhouse gas lines are right in this, somewhere around the 10 to the minus 5 meter wavelength range, or 10 micron wavelength range, where they just don't like, they reflect this radiation back to the Earth again. So that's what we're up against here, and it's all caused by atmospheric carbon dioxide and what we could call carbon dioxide equivalents. That is, something has the equivalent of part per million of carbon dioxide, may take only a part per billion to be equivalent to carbon dioxide, but there just isn't quite as much of it. So we're essentially normalizing all of the different greenhouse gases and considering them as carbon dioxide in order to look at what the overall effect on the planet. I'm guessing almost everybody in this audience has seen that curve of the atmospheric carbon dioxide at Mauna Loa that's readily available on the National Oceanographic and Atmospheric Administration Earth System Research Lab website. And you can track that up to about 2019 and notice that, my goodness, it's up at about 412, 413 parts per million. And I'm kind of an old guy. I'm 76 years old, and that means I was born back in 1943. And you look at the bottom, and these atmospheric greenhouse gas concentration has increased by over 100 parts per million in my lifetime. And that's almost 30%, given that it's gone up from about 310 to 410. So I don't know if there may be a few other old timers online here, and if so, welcome, glad to have you. Anyway, the 1, 2, 3, and 4 you're looking at there, they represent some of the options we might have. And number 1 is not acceptable, because the scientific community is now pretty much in agreement that somewhere between 425 and 450 parts per million could represent uncontrollable increase in temperature. And at this point, even if we cut all of our carbon dioxide, other factors that we've cut loose will continue going. And we just may have some serious problems. And looking at what some of those serious problems might be, there's this Job One for Humanity website. It's a pretty well written analysis by a large number of scientists have signed on to it. And, you know, I mean, I happen to live, have the good fortune of being able to live in next to the ocean down here in South Florida. And, you know, people down here, they seem only concerned about sea level rise. They have no concern about the other stuff that's going on. And we're going to look at some of the other stuff that also is attributable to global climate change. And look at that for a little while longer. And then when we see some of these things, we will move on to some things that can be done remarkably quickly and in a reasonably cost-effective manner in order to change all this crazy stuff. The irony is that this I'm sorry about my throat this morning. The irony here is that, well, we'll come to the irony. I'm having problems here. It took a long time for me to log in. Somehow the bandwidth or whatever was happening was slow. And anyway, so I'm settling down now. Anyway, when these tipping points are crossed, and we're going to look at 11, and I've heard of several others since looking at this, but these 11 pretty well make the case of things that are happening out there. And these are things that can happen if we let it go. And the one at the bottom, if we just totally ignore things, is extinction level climate destabilization. That doesn't sound very good at all for you or me or our children or our grandchildren. So let's look at what these tipping points are. One of them is total atmospheric water vapor, and very simply, the warmer the planet gets, the easier it is for water to evaporate. So we end up having more water in the atmosphere, and water is a fairly significant greenhouse gas. The thing about it, though, is it comes and goes, and in terms of relative humidity, in terms of total water vapor in the air. We've got some numbers here for those who want to pursue that a little further if you order the slides. Bottom line, though, is that atmospheric water vapor can cause additional rain, but in the process of being hotter, it can also cause additional evaporation. And so more floods, stronger winds, things like that. Tipping point number one. Let's look at number 2 and 3. Melting ice. This is the effect of melting ice is that when ice on land melts, it adds more water to the ocean, increases sea level. But when the seawater itself, it warms. Water has a positive temperature coefficient when it gets above 4 degrees C or 39 degrees Fahrenheit. And it means as the water gets warmer, its volume increases because it has a positive temperature coefficient. So maybe almost 80% of the sea level increase is due just to the temperature increase of the water, and 20% is due to the ice that's melting in. And of course, there's this shelf down off Antarctica that's the size of Florida that's just thinking that it's maybe going to break off in another, who knows when, nobody really knows. It seems that things are happening faster than had originally been thought. And of course, when you melt ice in seawater, fresh water is much lighter than salt water, so the fresh water floats on the top. So the total amount of melting ice That's the problem. There's your sea level rise. The albedo effect is the fact that sea ice reflects sunlight back away from the Earth's surface. And if there's no ice, then almost 100% of that sunlight gets absorbed. And of course, if it absorbed, there's 1,000 watts per square meter. So that's a lot of heating for heating the water. And of course, when the water gets warmer, it melts more ice. And the more ice that melts, the more heat can be absorbed, and on and on and on it goes exponentially. So that's a serious problem. Tipping point number 4, melting permafrost. Well, methane is trapped in permafrost, and if it's released, it's 20 to 100 times stronger than carbon dioxide as a greenhouse gas. Now, why 20 to 100? It's all a matter of the time frame over which you measure the effectiveness, because ultimately the methane decomposes into carbon dioxide and water in a matter of 5 to 10 years. But initially, the methane is much, much stronger than carbon dioxide as a greenhouse gas. But once it breaks down, then it breaks down into carbon dioxide, where it, so therefore, depending on how long of a time frame you're measuring over, the folks are now saying it's 20 to 100 rather than strictly 20. So, gee whiz, now you get more greenhouse gases from the methane, which causes more melting of permafrost and more release of methane, and on and on and on exponentially. Pretty serious threat. We'll see another threat that maybe could come from the permafrost melting in addition to this release of methane as we move on through the tipping points. Number 5 is plankton dying. This is not a coronavirus in the back, by the way. That happens to be a plankton. And they absorb carbon dioxide and they release oxygen. They're our source of oxygen. 80% of our oxygen supply almost from plankton. And the warming and carbonization and acidification of the oceans is causing the plankton to die. And that disrupts the food chain for fish, results in disruption in the oxygen cycle. Yeah, we don't even think about a problem with oxygen, but if this thing gets too extreme, then we're going to start losing oxygen as well. It doesn't get produced from the plankton, from eating the carbon dioxide. So interesting problem, something we'd like to avoid if we could. Then there's transfer of ocean surface trapped heat to lower levels. Sometimes usually the coolest water is the densest water, and that's at the bottom. But under certain conditions, that surface water can circulate down to the bottom and make instead of a circular motion on top, it's a vertical circular motion. And it can increase the overall heat in the ocean. And then when the warmer bottom water rises again, then it causes a more rapid surface temperature rise. And that, of course, can also happen exponentially. And if you have more rapid surface temperature rise, more evaporation, higher winds, more hurricanes, all those things that are caused by higher surface temperatures of ocean water. Number 7, loss of forest. We've had a lot of that lately. Talk about the Amazon, talk about California, a lot of places. And everybody knows that you generate a lot of carbon dioxide and you lose a lot of trees that do their fair share of absorbing carbon dioxide. So we need those forests out there, and they got to grow back. We got to be careful with them. Release of carbon from soils, number 8. Hotter that soil gets, more evaporation releases carbon. And that increases atmospheric carbon dioxide as well. So again, another exponential issue. This is one that most people don't think about. Changes in major ocean currents, slowing down of the Gulf Stream. You know, when we start adding a lot of extra temperature gradients and concentration gradients, we start affecting these currents that for the most part have been affected by Coriolis forces, but now we've got other competing forces that can change the ocean currents, and that can affect weather, and that can affect crop yield. And so something we need to try to prevent. And number 10, potential for global pandemic. I guess we kind of know what that is now, don't we? And what we don't realize is that we don't know what's stored in the frozen ice up in the permafrost. And there's an awful lot of that in northern Russia across Siberia. And when these melt, these pathogens may come back to life. Well, come back to life, may become exposed. I guess it's pretty well understood now that, for example, a coronavirus is not exactly alive, but it does like to grow when it gets in the right kind of an environment, like a person's lungs. So imagine if we melt this permafrost and every 2 years we have a new pandemic we have to deal with. That's something we kind of need to make sure that doesn't happen. The possibility is certainly out there. The scientists have recognized that as a possible thing. And number 11, total weight of rising seas and melting ice shifting. You know, think about it. Everything has some kind of a coefficient of thermal expansion. And as the rocks and the water and whatever, you know, the mantle of the earth, if it warms up, it's going to expand. And expansion of that mantle may be 1 degree C, but when you're talking about over many, many thousands of miles of 1 degree C, that shifting of maybe 10, 1,500 feet over thousands of miles can cause some pretty major disturbances. So more things that are out there that add to the problem of rising sea level rising, okay? So there's the problem, folks. Let's look at the solution now. That's a little more encouraging to look at the solution. I wanted to get the problem out of the way first. And now let's look at what we as design professionals can do to be a part of the solution. How do we make electricity? Electricity, I want to take a look at the amount of greenhouse gases due to electricity and what we might do about it. So these are the sources of the United States electricity in 2018. And notice that nuclear and renewables account for almost 37%. Renewables themselves, 17%. So there's a whole lot more than the 2 or 3% that was the case back in around 2000, 2001, whatever. Natural gas is 35.6% of the electricity is now produced by natural gas. Notice there's no oil there at all. And coal is, whereas Florida used to make a lot of electricity using crude oil, coal is 27.8%. Now that's the amount of electricity produced by these sources. Let's take a look at the amount of greenhouse gases produced by these sources in proportion. And here you see that, wow, there's just 2 big-time contributors. Coal contributes 65% of the greenhouse gases that come from the electrical generation sector. All right, and that's all of the electricity that's being generated in the United States. 65% of the greenhouse gases come from coal, and 33% come from natural gas. So even though natural gas, we're making more electricity with natural gas, the amount of greenhouse gas released by burning natural gas is less than for kilowatt hours worth of electricity made by coal. Natural gas takes about 0.8 of a pound of natural gas to make a kilowatt hour, or not 0.8 of a pound natural gas, but a kilowatt hour made by natural gas gives off about 0.8 of a pound of greenhouse gas, carbon dioxide, whereas coal is up somewhere in the range of 2.2 pounds. Don't quote me on those numbers, but it's higher. You can, just by comparing these graphs on the last 2 graphs, you can get the relative amounts. So now, where does this electricity go? And what is the consumption by sector? The reason we're drawing these pictures and taking a look at it is, one, because the engineers and architects love to see pie charts. And the second reason is simply because it's kind of hard to know where to go unless you know what the options are. So here we see that electricity is 37% of all energy consumption in the United States. Transportation uses 28%, industry 22%, residential commercial 10%, and other 3%. So you can see the residential and commercial, the electricity, of course, goes to all of these sectors one way or another. All the electricity made by electric power company is not used by the power company, it's used by the rest of these sectors. So the 10% in the residential and commercial means other than electricity. Okay, so that means the natural gas is used for heating, for example. Industry, the 22%, there's still some coal, oil, natural gas, a number of fossil fuels are used. And for that matter, there is a certain amount of natural gas that goes into the atmosphere from industry, and that counts like a factor of 20 or 25 in terms of its relative effectiveness as a greenhouse gas. So these are the sectors to focus on. If we can pay some attention to electricity and transportation, for example, we could put a big dent in the amount of greenhouse gases generated. Well, let's take a look. What about the actual greenhouse gases? 3.29 trillion pounds per year for transportation alone. These gasoline-powered cars, okay? So that should ring a bell. Maybe we can do something about that. Electricity, 3.17 trillion pounds per year. My goodness, we know there are some forms of electricity generation that don't give off any greenhouse gases, like solar, wind, and nuclear, for example, and hydro. So, and I'm not necessarily endorsing any of those because we're going to let the economics of those various sources determine which one are going to be used. But in any case, none of them give off greenhouse gases as they're operating from day to day. But 3.17 trillion pounds a year from electricity. Notice then that 28 and 29%, that's the full 57% of all greenhouse gases are attributable to just the transportation and electricity sectors. So if we could do something about those two sectors, and at the same time be working on the other sectors, but if we do something really drastic on those two sectors over the next 10 years, we can make a pretty big dent in the amount of greenhouse gases that are given off, can't we? Okay, so let's take a look at transportation sector. Where does it go? Well, personal vehicles, 58% of that. Hey, they burn gas, don't they? Most of them, not the Teslas. Not the a lot of plug-in hybrids and things. The big trucks, 23%, air 9%, ships 2%, rail 2%, other stuff. That's mostly off-road vehicles, construction vehicles, things like that. For the other 6%. So we know where it goes. So we know what to look at. Personal vehicles, large trucks, ships. Airplanes, interesting. Can we reduce the pollution from airplanes? Well, there's ways a lot of people are thinking about how to do that in terms of biofuels and maybe even electric airplanes. There are actually some electric airplanes out there. We're going to take a look at some of the specific solutions in a little while here. Let's look at some worldwide consumption by energy source, just so we get an overall picture of what's out there. Notice it's a logarithmic scale on the vertical. And notice that the three on the top, the three fossil fuels, coal, oil, and natural gas, have been relatively flat for, well, the last 30 years or so. Okay, increase ever so slightly. On the other hand, take a look at the hydro. That's the one that's blue. That's been going up since about 2005. And look at the green one. That's our renewables, which is mostly, and notice that's not, hydro has been separated out from the renewables. But the green one, up to date to 2018, and that green was a projection from back in 2014. And that projection, by the way, that was one that I did just to satisfy my own curiosity of where things might go from 2014. And notice that green one is really climbing fast. That's your wind and your hydro mostly, or wind and photovoltaics primarily. So just follow that out for a ways. And how long would it take at the current growth rate for our renewables, other renewables, the green line, how long would it take before it could catch up to the fossil fuel? And the answer is somewhere around 2030. So let's develop, let's look at a couple more pictures, and then I want to do is develop a scenario for you to take a look at. Actually, here's the scenario right here. Let's say we start at 2018. And in 2020, we reduce, and this is scenario one, and the idea is to just reduce transportation, electric generation, and industry. And the transportation and electric generation and industry is the orange, and the blue is the rest of the energy sector. And if we have an aggressive program to replace all electric generation with the renewable generation, and to replace all transportation with electric transportation, and we got to look at whether we can afford to do that. We're going to do that, but this is a scenario that we're going to offer as a possibility, and then we want to see how real this possibility could become if we got serious about it. And we're going to compare it with some of the ways we're spending money right now. Well, you notice that by 2029, there's no more orange stuff left. It means that in a 10-year period, we will have gotten rid of all of the carbon dioxide accountable to transportation, electric generation, and industry. Well, we've left everybody else off the hook. But then again, my goodness, there are zero energy buildings out there for us to design. So there's no reason why that blue part, why those blue parts of the curve have to stay the same size. There's no reason why we can't start reducing on them as well. So let's look at scenario number two. And this includes a moderate, that is a 5% annual reduction in the other sources. And notice that we can go down here less than 1 gigaton of annual emissions instead of 5, which is about where we're at right now. That's an 80% decrease using this scenario by 2029. All right. Again, we haven't figured out whether we can afford it or not, but we do have an 80% decrease here. All right, now let's take a look at scenario number 3. Let's say we really want to get aggressive and we want to knock off, we do the same thing with the transportation, electrical generation, and industry, get rid of all the CO2 from that by 2029. This is in the United States, by the way, and one might argue, well, gee whiz, the Chinese, though, they're the ones who really pollute. Well, the United States is the largest per capita generator of greenhouse gases on the planet. And the Chinese are already ahead of us in reducing their per capita greenhouse gas production. So they understand. They don't believe in any of the myths that are on that previous slide. And they are building wind and, and solar like crazy. And a lot of other countries, the Europeans and whatever. We'll see later who's making the biggest difference. But for the moment, scenario 3 looks pretty attractive because we're down reducing greenhouse gas emissions by 90% by 2030. And The question is, can we do it? Can we afford it? Is the technology there? And the answer is yeah. Like, it really is. It's there, and it is cost effective. And not everybody knows this. So we need to pass this word along to our friends. So let's take a look here at some of the economics of climate change. Let's just say that we're going to transition electrical generation to renewable. What do we need to do that? Well, we already know what we need to do. For coal, we need to replace 1.15 trillion kilowatt hours a year with renewables. For natural gas, we need to replace 1.47 trillion kilowatt hours with renewables. And then we're going to have to install storage because, natural gas, you can burn that stuff anytime. Coal, you can burn it anytime. But the sun only shines during the day, and the wind is a little bit unpredictable how it blows. So we're going to need some energy storage to smooth out some of the humps in the process. So we need to include the cost of some energy storage as well. And according to a study by the National Renewable Energy Labs way back in 2012, it'll take about 100 million kilowatts of storage. And that's 100 million kilowatts, by the way, not kilowatt hours. The number of kilowatt hours, this is just instantaneous power available for storage when a cloud comes over the sun, for example. The number of kilowatt hours is probably more like somewhere between 400 and 800 million kilowatt hours. But it turns out that that's affordable too. Just look at the cost of eliminating coal. To eliminate all the coal and replace it by renewables, and gee whiz, we'll lose some jobs, but we'll improve the environment. And everybody who's mining coal either could be put on pension, or they could be hired by the renewable industry, or they could be hired by the energy storage people. There will be lots of jobs out there. There are a whole lot more jobs in renewables right now anyway than in coal or even in oil or natural gas. So the jobs are there in renewables, and there will be a whole lot more, probably 10 times as many within the next, say, 10 years. So let's just say that 80% of the renewables are replaced at utility scale, big 100 megawatt solar farms. All right, that would cost about $1.72 trillion. And if we put the remaining 20% on residential and commercial roofs, that would cost about $0.43 trillion. So for a mere $2.15 trillion, hey, that's just about what we're spending just now for relief from this virus, isn't it? Just about 2.15 trillion. And I'm proposing that we do this over a 10-year period, so that's only $215 billion a year to eliminate coal. Eliminating natural gas, $275 billion a year for 10 years. Can we afford it? The U.S. gross domestic product is 22.8 trillion. All right, and the annual military budget is 700 billion. So can we afford it? And keep in mind that most of this investment is going to be done by you and me and industry, because we're going to find out that, in fact, these are good investments. They are money makers. The levelized cost of energy, for example, from solar or wind is actually less than the levelized cost of energy from natural gas. Natural gas is up a little over 6 cents, and solar and wind are down below 6 cents a kilowatt hour for the levelized cost of energy, meaning that's what you have to charge for the energy that you generate in order to pay back your investment in the technology. So over the life of the plant. And nuclear now, for advanced nuclear plants that are proposing to build, the only thing is that they're up at 9 cents a kilowatt hour. So that's almost 50% higher than the cost of solar. So again, like I said, we'll let the economics dictate what makes most sense. The utilities are not going to invest their money in things that don't make economic sense. So we'll see what happens. I can tell you that my local utility here, which includes Next Era Energy, they are building solar like there's no tomorrow. So they understand they can build solar for about $1.50 a watt. And whereas rooftop is still going for around $3 a watt. So large utility scale solar is the least expensive electricity that utilities can make right now. So why would they not want to do that? Okay. So let's look at energy storage. I hope you all can read that yellow. It looked up fine on one of my screens, and then on another screen I couldn't read that yellow too well. But anyway, there's a lot of ways of storing energy, including pumped hydro, compressed air, capacitive storage. There's not much commercially available capacitive energy storage yet, but it's on the way. Flywheels are commercially available for energy storage. There's at least 10 different battery technologies out there. And as we increase the number of electric vehicles, and I'm going to make an argument for why we need to do that very soon, the battery capacity of an electric vehicle, if you've got a lot of them, it can store an awful lot of electricity. We happen to own a plug-in hybrid, which has a battery storage capacity of 17 kilowatt hours. That's a fair amount of kilowatt hours for a normal house. You multiply that by 30, that's maybe 60% of the monthly electric bill in a typical relatively small house. So 17 kilowatt hours, if the car doesn't need it, and if they can sell it back to utility at a time when utility needs it, and if there's 100 million of these vehicles on the road, wow, amazing. Not necessarily on the road. Let's just say that a bunch of them are in parking lots plugged in and able to sell instead of just buy. So interesting possibilities, and we're going to see that happening over the next 5 years in fairly large scale. And I'm guessing that if there's any electrical engineers online here with the webinar, that you very well likely will be a part of this design, because you're going to have to do load calculations and things to make sure that the additional 6 kW of electric vehicle charger is still within the capacity of the existing service or whatever. And another final thing is just lifting cement or steel. You can imagine a big crane that lifts a huge air conditioning unit or a huge whatever it is onto the roof of a 30-story building. Lifting that heavy thing up, that you have to pump some electricity into that if it's done electrically. But then imagine letting go and letting that thing fall again with dynamic braking and generating electricity. Then you can get most of that electricity back, maybe 80 to 85% of it, with a pretty efficient system. So instead of taking all the space it takes for pump hydro, you have a circle of these huge cranes that can almost fit in a neighborhood and do neighborhood energy storage just by raising weights uphill. So in any case, anything is commercialized means it's cost effective, because otherwise you won't be able to sell it. And right now, storage is costing about $125 per kilowatt hour in the United States for large scale storage. And so therefore, let's look at an example of a design for 100 megawatt hours, or 100 million kilowatts, okay, and that's more than 100 megawatts, okay. That's 100 million thousand watts, or 100 billion watts. And if you want to provide 100 kilowatts for 4 hours, then it's going to have to store 400 million kilowatt hours of energy. All right, so at $125 per kilowatt hour, that's $50 billion. what seems like a lot of money, but compared to the kind of money that's being thrown around right now, it's peanuts. And especially if you spread that over 10 years, that's $5 billion a year. We spend more than that on cosmetics. So, and furthermore, storage costs is going down. It's been coming down for the last 10 years. New technology are continue to come online. So, and by the way, this is available on a daily basis. You can discharge that 400 million kilowatt hours whenever you need it during the day or night, and then pump it back up again whenever the energy source is available, whether it's wind or solar, but probably a combination of the two. All right. So there's going to be some short-term and there's going to be some long-term storage. You need short-term when a cloud comes over the sun, and in minutes to an hour or so will take care of that. But then you need longer-term overnight. So the total amount of storage will be some combination of these, and the price is going to be relatively insignificant compared to the price of the energy sources themselves. So this is encouraging. It's very encouraging to me, folks, because before I started researching this material last August, and I spent an awful lot of time on it, I was feeling pretty hopeless, and I am not feeling hopeless anymore, because I am hoping that the rest of us will pick up on this and find out that it's a fine way to make money by saving the planet. What could be a more honorable way to earn a dollar than by saving the planet? So let's take a look at some specifics here now, okay? First thing I want to do is look at zero energy buildings. And I have to tell you, I spent almost 2 hours yesterday sitting in on a webinar where they talked about a zero energy school building they built here in Florida. And what an impressive piece of work that was. So I just want to give you an idea of what's involved in building a zero energy building. And, you know, a zero energy building is not a little storage shed that doesn't use any energy. It is a building that uses energy, but the net energy it uses is zero. So if you take a site boundary, and this might be a group of houses, it might be a group of buildings, whatever, maybe a microgrid. Anyway, they're energy users. You have on-site production of renewable energy, and in fact, it's also possible to have this production of renewable energy going on off-site in a state that allows third-party generation, where the folks in the green rectangle build the system off-site that will make enough renewable energy to offset the energy that comes in from the utility, which is in the pink box. So the energy for this building comes from renewable on-site and off-site energy from the utility. And it's very possible the utility itself will have a significant part of its energy renewable, okay? The key with the design of these buildings, though, is make them incredibly energy efficient. And to a great extent, what that means is making them infiltration well below the code required values, and then use very efficient heat exchangers to bring in outside air. And that turns out that's healthy and all kinds of things, and that's covered in courses on zero energy units. So in any case, this is just the definition in the way a zero energy unit is defined. So let's look at some of the systems that might be involved in these zero energy units, okay? And first, you need energy conversion factors, because imported electricity you buy from the utility, it takes 3.15 times as much fossil energy to make electricity than the energy you get out. In other words, for every every BTU of electrical energy, or every kilowatt hour of electrical energy you make, it takes 3.15 kilowatt hours of fossil energy to make it. All right, so if the imported electricity has that, and this is on average around the country. For some utilities, it's smaller and some are bigger, but this is the United States Green Building Council has zeroed in and agreed on these numbers for the source energy conversion factors. Even so, the exported renewable energy, electricity is electricity. My light, my lamp, my air conditioner doesn't care where it comes from, just so it gets it. So therefore, the exported renewable also gets a 3.15 source energy conversion factor. Natural gas 1.09, and as you can see down the line, steam 1.45. A lot of these are things that we wouldn't normally be using. Coal 1.05, and that's simply because coal is not going to be used to make generate electricity on site. It is, if anything, it's going to be for process heating or industrial, where 95% of the heat from the coal is probably contained in the processing. So using these source energy conversion factors, then we can look at the energy into the building and the energy out of the building, okay? And then you start out by estimating the direct building energy usage. So let's try it. Let's do an example. But let's get down some of the numbers first so we understand how to do the conversions, and because everything has to be expressed in the same units. Well, we all know, because this is something we committed to memory when we took our first physics course in high school. We all, of course, remember that 1 BTU will raise the temperature of 1 pound of water by 1 degree Fahrenheit. That's the sort of thing we'll take to the grave with us. We will never forget that. We may forget our own name, but that's something we will always remember. A kilowatt hour directly converts to 3,413 BTUs. So if you use a kilowatt hour of electricity in your electric water heater, where it goes strictly into heating a heating element, which strictly heats the water in the water heater, then you're going to get 3,413 BTUs of water heating with 100% conversion of a kilowatt hour of electricity. If you're burning natural gas, a therm is 100,000 BTUs. A barrel of oil, that's 42 gallons, and that's 5,800,000 BTUs for a barrel of oil. And a gallon of fuel oil, number one, is 137,400 BTUs. So those are your common kinds of energy sources you might have for a presumed desired zero energy building. So the first thing to do is to list all the energy sources and the estimated use of them, and then convert them all to source energy equivalents. Now, for most residential, you probably just have 2 of these. You might have one for, if you're up north, chances are you got natural gas heating, and maybe you've got electricity, and maybe you have natural gas cooking, and maybe natural gas water heating. So you need to convert your electricity into BTUs and your natural gas into BTUs. So let's take a typical dwelling unit here. If this dwelling uses 75 kilowatt hours a year and 500 therms of purchased natural gas, again, this is fairly typical, then we have to convert the electricity to BTUs, which is 25,597,501.33166, but I rounded it off. And then you next thing you do is convert these electric BTUs to source energy. So we have to multiply by 3.15. That gets you up to 80,600,000 some odd BTUs. Then we look at the 500 therms of natural gas, and using a source energy conversion term of 1.09, 500 times 100,000 BTUs per therm is 54,500,000 BTUs. So therefore, the sum total of the 80,632 and the 54,500 is 135,132,125 BTUs of source energy being used by this building. So if we want to offset this source energy with PV, and that's the whole idea, that this is the source energy, estimated annual source energy for the building. So in order to turn this into a zero energy building, we have to replace all of this with renewables. And generally the easiest renewables to do in a neighborhood is photovoltaics. Wind is not quite as popular in the typical neighborhood. All right, so we just have to estimate the size of the PV system. Well, let's take a look at how to do that. And again, let me remind you all that, oh, and by the way, we'll be, if you have a question, please make a note of it, because we're going to have a question and answer session at the end of the session. Okay. And also remind you that these slides are available on the website in this PDF form, and no charge. Free for the asking. Just go to the PDH source website, and when you go there to get your certificate for completion of the course and take your quiz, if you need to take a quiz, you'll be able to you'll be able to download the slides as well. Again, no charge. We're happy to get them out. Use them as you wish. Don't worry about copyrights. I'm happy to see somebody else use this. It's important stuff. We need to convince our friends that we're on the right track here. I mean, we're talking science here. Multiplication, division, addition, subtraction. It's about as complicated as it gets. Okay, so let's determine the size of the PV system. How do you do that? Well, you call a PV system designer and say, hey, I need this many kilowatt hours. Well, a typical, and I say typical, okay, south-facing array can produce about 1,500 kilowatt hours a year for every kilowatt of array. But it depends where you're located. If you're middle of the desert, you might be able to do 2,200 kilowatt hours a year per kilowatt. And if you have a tracking system, you may be able to do even better than that. The thing about tracking is you have to take up more space because you can't let one part of the array shade another part, so the rows have to be spaced further apart. All right, anyway, if we do BTUs on this, this is the number of kilowatt hours we can get for a kilowatt of photovoltaics. That means a kilowatt of photovoltaics will give us 5,119,500 BTUs per year. All right. So now go to source energy. You have to multiply by 3.15, and that gives us 16,126,425 BTUs per year for every kilowatt of PV. So how many do we need? We need 135, 132, 125. So it just boils down to a mere 8.38 kW of photovoltaics. And the average 1,800 square foot house, if it's properly designed, excuse me, you can fit this on the roof. And here's why. Typically, the efficiency of an array is about 20%. All right, so that means if you get a 1,000 watts per square meter, it can convert 200 of them to electricity for every square meter. So if you have 8,380 watts, then 200 watts per square meter, it's 41.9 square meter, which is 451 square feet, which is 10 by 45 of south-facing roof space. Using 300 watt modules, you need 28 of them. And of course, you have to check the dimensions of the modules, but the dimensions are usually about 1 meter by 1.5 meters. And you fit them on a roof, just like that, piece of cake. And it costs for residential or whatever, somewhere in the neighborhood of $3 a watt. The cost for the electricity life cycle cost over the life of the system, probably going to cost you about 6 cents a kilowatt hour. Pretty cheap way to make electricity. Okay, so that's a design of a zero energy building, just like that. What do we take? 10 minutes to do it? Take a little longer than that, of course, when you actually draw up the pictures and get the specific dimensions of the unit. But let's look at what's out there for these zero energy buildings. For example, the heating, ventilation, and air conditioning systems. The Mitsubishi people now have an inverter technology heat pump that will operate down to minus 13 degrees Fahrenheit. Once upon a time, even 15 years ago, a heat pump operating down to 40 degrees Fahrenheit was good. But below that, you had to have auxiliary heating. This thing will operate down to minus 13 Fahrenheit, and it has SEER up to 33.1. And that's double what a lot of the EERs are right now. Some of them are up to 20 if you really go for a good unit, but 33.1 for an inverter technology heat pump. This is one where it's basically a mini split system with 4 separate zones. And of course you have 8 zones, you use 2 systems and do 8 zones. So you get additional efficiency because you can control them zone by zone without having the air return having to flow through other zones that are being shut down or run at a warmer temperature. You know, when you want your bedroom to be cool at night, but you don't care if your living room, you just don't want it to get moldy, you can run your living room at a higher temperature than your bedroom. So beautiful ideas for design here. If you want to control humidity, now here's where we're talking about ventilation. The ventilation is purposeful, carefully designed and controlled ventilation where you do a heat exchanger and you vent the cold air from inside, the air conditioned air, but that cools down the warmer outside air on the way in, or vice versa if you're in a heating environment. And these things are now available with efficiencies above 90%. So you can meet the ventilation requirements and in fact come up with a whole lot more healthy environment by building the zero energy building. And if humidity control is not quite as important, which is in some of the northern, down here in Florida, the only option would be energy recovery because it's so humid. But if you don't have significant serious humidity, then you can go with heat recovery ventilators and they'll work. So here's some equipment. It's there on the market. Go out and buy it, install it. It's okay. You can do it, whether it's for new or for a retrofit. How about domestic water heating? How can we improve on it? Well, there's always solar water heaters, but guess what? Using a water heating heat pump is probably more efficient than using a solar water heater, and especially if the occupancy is not occupied all year round. Because what do you do with your excess solar water heated water if you're not using it? You can't sell it to the water utility, can't sell it to your neighbors, so it just kind of stays hot and that's it. No money deal at all. Whereas if you have photovoltaics on your roof and you're not living there, the PV doesn't care. It's going to make the electricity anyway. And if the unit is using a whole lot less of it, that means a whole lot more gets sold back to the grid. So times have changed. Once upon a time, it was much more cost effective to have solar water heater. Now, it turns out you got to do the math because it may very well turn out that it's more cost effective to use photovoltaics or a water heating heat pump or a water heating heat pump with photovoltaics to power it. Why the water heating heat pump? Simply because it uses compressive heating. And so you can produce about 3.5 kilowatt hours of heating for every 1 kilowatt hour of electricity. That means a coefficient of performance of 3.5 on the heat pump. That's the heat pump right on top, by the way, the little compressor unit. Makes a little humming noise when it's running. And these things are maybe, I don't know, you have to get your price from your supplier, but it turns out, bottom line is over the life of the system, they're very cost effective in terms of if you're looking at saving kilowatt hours, it might be worth, well, first of all, you're talking about the amount of source energy you're using to design an efficient envelope and equipment. So what are the trade-offs? Well, if you can make the building more efficient, you don't need as much solar. So you start adding efficiency until all of a sudden, say you got insulation and you're going from R19 to R38, and the cost of adding that additional R19 of insulation is more expensive than adding a little bit more photovoltaics. So you don't add the extra insulation, you take the least expensive alternative. And you just go through your entire design that way, using the most cost-effective alternatives. And in a lot of cases, you start out with energy efficiency. Like I said, one of the most important things is infiltration, and there's some really fancy methods now, and they've come up with to seal off the building so that you just don't have these in the winter where you look at the thermograph of the wall and you see all these cold spots around the electrical outlets and so forth. So we're going to take a look at different orientations of photovoltaic arrays, because you can't necessarily always set it up so your PV looks south. But if it looks west, that can still be okay. You will decrease the performance, which will increase your cost per kilowatt hour, but it still is an option. And you can always make the array, well, maybe you can make the array size bigger if the orientation is not optimal. Usually the best orientation is to be tilted at about latitude, but it turns out that it's not that critical. And let's take a look at what we've got here for Albany. Photovoltaic array, okay? Let's say that's facing south at 60 degrees. Well, let's say it's facing south at 30 degrees. That gives us 100% of the annual max. In other words, that's where we make the most electricity in Albany, as if the array is facing south at an angle of a tilt of 30 degrees up from the horizontal. Okay? If we tilt it up an extra 15 degrees because the roof is at a 45-degree slope to make sure the snow falls off, we only lose 1% on the year. So nobody's going to fuss about that. It's okay. It'd be way too complicated to try to tilt something at 30 degrees when the roof tilt is 45. And even at 60 degrees, the loss is only 7% on the year. If it's flat, you lose 13%. If it's vertical, well, here you lose 33%. So you probably don't want it vertical. If you're in Germany, yeah, sometimes you can have an array vertical, but you have to be pretty far north to have cost-effective vertical orientation on a PV array. But you can see the different orientations. 10-degree slope facing southwest, 25-degree slope facing southwest, and the numbers are what percentage of the maximum are you achieving with that particular array orientation. It's interesting to look at, for example, facing west and facing east with a, well, in Albany it doesn't make a whole lot of difference. In other areas it does. The thing is, by doing a simulation of the performance of the photovoltaic array, you can figure out exactly what kind of orientation you need, slope. Yeah, it makes sense to design buildings that have south-facing roofs because it takes less photovoltaics on a south-facing roof to achieve the zero energy performance requirement. Okay, so if you're starting from the beginning, what a good idea, if you're starting from the beginning, to actually build a building with the roof facing south. I'm hoping it'll be a little bit easier to convince owners that this is the only way to go these days. Because I can tell you that when I was trying really hard 10 years ago to convince owners that were building new buildings to come up with a goodly amount of 600, 700 square feet of south-facing roof, there was a lot of reluctance because people wanted to do these fancy dormers coming out and 14 different roof orientations and lots of different angles and no room for PV at all on the roof. Sure looked fancy. There's no payback on a roof like that. And people just didn't seem to understand. They didn't seem to care. And folks, I am imploring you to focus on this and almost tell people, I'm sorry, I won't design this building for you unless you are willing to make it efficient. Why should that be on your head? You know, find people who are willing. Okay, zero energy. Here I'm preaching. I'm not supposed to preach. I'm an engineer. I just happen to have been in the energy efficiency and renewable energy business for the last 40 years, so it kind of wears in a little bit. Let's say you want to build a zero energy building, okay? How much extra is it going to cost? Well, guess what? Here's six cities in the United States, Atlanta through San Francisco. The extra cost to turn a zero energy building in Atlanta would be $19,548. The savings on your electric bill, your energy bill, be $152, and your extra mortgage payment be $100. So there you go, $52 a month savings, starting with day one for a new building. Okay, Baltimore, higher savings, lower initial investment. So therefore the monthly mortgage increase is smaller. So here we're looking at $86 a month. And you don't pay taxes on that extra money either. This is like an extra $86 of free money that I used to call it tax-free return on investment. If you pay 20% on that, divide by 0.8, and all of a sudden you're up even higher of what the value of that would be if you consider the taxability of it. It's like tax-free municipal bonds almost. Chicago, $71, they're good. San Francisco, look at that one. 100 and, what is that, 9 there, and 117, $126 a month saved by building a zero energy building. It's incredible. So why would anybody not want to do this? I ask you, why? You can do this. You can design these and save lots of money. And the extra bonus is you're saving the planet. Who would not want to do that? These apply to retrofits. Retrofits are a little harder if you got a lousy roof and lots of bad insulation, but you can make the buildings a lot greener, most of them out there. You know, get rid of the fossil fuel heating and use renewable electricity equipment. Refrigeration, make it more efficient. All this stuff. LED lights, wow. Better doors and windows. Boy, we spent a lot of money this last year. Almost $15,000 to get hurricane windows installed, but boy, they are nice. They keep a lot of the noise out. We can't see out them because they're all full of salt blowing in from the ocean, but who wants to see out windows anyway? You plug up the air leaks in the old buildings, you can do that. You can upgrade insulation, okay? Here's your list. You to get this right for the, I mean, these ideas are out there all over. I'm just trying to put them all into one fairly concise presentation. You know what I want to do? Hold on just a second here. All right. At some point, if anybody has a question, I think you're able maybe to type that in. And from time to time, I'm going to look at my drop down that will tell me the questions, and we can then talk about the questions. So at this point, if you want to start asking questions, feel free to type them in and just find where the Q&A box is. It may be across the top of your screen. That's where it is on mine. It may be near the bottom of your screen. But wherever that Q&A box is, feel free to type in a question. I'm going to be looking at that from time to time and see if there's any questions and answers. Right now it tells me there's no open questions, okay? So, how do you do all this analysis for the buildings? Well, again, those of you who are involved in MEP, for example, and designing energy efficiency, trying to make sure it's compliant with the energy code, you're probably familiar with the various computer programs. But you don't need to guess. You put in the dimensions of the wall, of the windows, the areas of the windows, the doors, the ceiling, and the whatever. And there's programs out there that analyze the building envelope, the building equipment, and the cost effectiveness. They'll tell you whether it makes sense to do what you're proposing to do. NREL has BE Opt. That's fine for single or multifamily, and it's free. Florida Solar Energy Center has been working on low energy buildings for years and years. I guess they probably started that division about 30 years ago. And that can be used for residential buildings and for tall buildings, condominium type buildings. And Energy Gauge is something you can download a 30-day trial if you like it. I guess BE Opt actually, there may be some cost for that. So let's keep that as, let's don't hold me to the fact that it's free. But you can look it up. Just Google it and find out. It lets you draw out your layout for the building, and out comes the energy analysis. So, and if you want to do the PV system performance analysis, National Renewable Energy Labs System Advisory Model, NREL SAM, you can download that for free. Just go to the NREL website and tell it you want to download SAM. Last time I tried to do an upgrade, I had some problems trying to get weather data in, and I gave up because I wasn't planning to design any buildings. But once upon a time, that was the tool that I used a lot in estimating photovoltaic system performance. Actually, I guess I did estimating photovoltaic system performance before SAM was even in, a dream in somebody's mind. But SAM is a very good program. It gives you a lot of good information, monthly performance, hour by hour performance estimated using typical meteorological year data and so forth. Okay, let's move from buildings to vehicles. And I think we're moving along at a reasonable pace here. We've got 11 more slides to go. Yeah, we're doing okay. We're going to make it. Let's look at some numbers about vehicles and fossil fuels. I'm guessing probably every single person listening in knows that burning a gallon of gasoline releases 19.6 pounds of carbon dioxide to the atmosphere. Well, maybe not, but now you know. Okay. If we make electricity with coal, for every kilowatt hour of electricity made with coal, an extra 2.2 pounds of carbon dioxide gets dumped into the atmosphere. If we make this electricity with natural gas, we make about 0.9 pounds of carbon dioxide per kilowatt hour. I had mentioned that earlier, that natural gas makes a lot less than coal, and then I see that I did guess right on the 2.2 pounds. And we've got 0.9 pounds here. Again, it depends on the efficiency of the generator. And if it's more efficient, then it releases even less carbon dioxide. But what a surprise, renewable generated electricity releases just about 0 pounds of carbon dioxide per kilowatt hour. Because there's no fuel. The fuel is the sun. All right, so now let's look at some gasoline powered cars, okay? They, on average, maybe about 25 miles per gallon. If that's true, that means for every 100 miles you drive a gasoline powered car, you're going to dump 80 pounds of carbon dioxide into the atmosphere. All right, now an electric car gets somewhere between 3 and 4 miles per kilowatt hour. Our plug-in hybrid, we've now got almost 2 years worth of data on it, and we are getting 3.5 miles per kilowatt hour on that machine. We're just absolutely thrilled with it. We drive it mostly around town, and we're getting, for the amount of gas we put in it over the almost 2-year period, actually a year and 10 months now, we're getting a little over 500 miles per gallon. So we're using electricity. Well, that doesn't mean we're not responsible for any CO2, but if we look at our local utility and their energy mix, they're doing pretty well. They're right about at the 0.9 pounds of CO2 per kilowatt hour. Actually, they're at 0.86, according to some numbers I looked up. Actually, they were looked up for me by a friend of mine who works for their renewable division. And so if we look at the 3.5 kilowatt hours, every 3.5 miles, we are responsible for 0.86 pounds of carbon dioxide into the atmosphere. But that means in 35 miles, that's 8.6. That means in 70 miles, that's still only 17.2. So it's the equivalent of a gasoline-driven car that's getting more than 70 miles per gallon. And as Florida Power and Light becomes more and more renewable, and they are working at it best, ultimately we'll be down, maybe, depending how long we keep the car, to maybe a few tenths of a pound of carbon dioxide per kilowatt hour. So not a bad compromise if you want to cut back on the amount of carbon dioxide you're dumping into the atmosphere. So for every 100 miles you drive, a natural gas powered electricity car, you're releasing about 25 pounds of carbon dioxide to the atmosphere, as opposed to closer to 80 with a 25 mile per gallon fossil gasoline driven car. And of course, the bottom line there is if by 2030 all of the electricity in the country is made by renewables, then the electric cars don't emit any greenhouse gases whatsoever. So that combination of making all of our electricity with renewables and driving electric vehicles says that we can take that entire chunk and get rid of that greenhouse gases. That's a lot. If you go back to that pie chart we had. Let's just look at a quick comparison here for 10,000 miles worth of renewable with an electric vehicle and gasoline. 10,000 miles with the renewable electricity is no carbon dioxide released. Use about 3,000 kilowatt hours, so the cost of operation is about $450 if you're paying 15 cents a kilowatt hour. Okay, if you're on a time of use rate, if you're on a commercial rate where you pay for kilowatts and kilowatt hours separately, and if you charge your car off-peak, you could be paying as little as down in the neighborhood of 8 cents a kilowatt hour. That is the energy rate for the condominium I'm living in right now, 8 cents a kilowatt hour. So instead of $450, it's more like $225 for fuel costs for a year's worth of 10,000 mile electricity. No emissions, and the batteries in the EV, if you're plugged in while you're at work, for example, they're available if there's a communication link and a bidirectional charger such that the utility can simply find your car, just like you can find your computer by its URL or by its whatever number it takes to identify your computer for people who do the virus protection, stuff like that. Imagine your electric vehicle parked at a public charging station, and imagine your local utility, the cloud went over the sun and needs some electricity, so it goes around and it talks to all of the cars that are plugged in electric charging stations and negotiates a deal to pay 15 to 20 cents a kilowatt hour, whatever, for a certain number of kilowatt hours while the cloud is over the sun to help stabilize utilities' need to meet everybody's demand. So this takes on automatically a negotiation between the car, maybe using parameters established by the driver, and the utility, so that the car can sell to the utility at a higher rate of per kilowatt hour, and then at night or whenever the utility has energy to spare, and maybe it'll be during the day when there's a lot of PV cranking out, then you can charge your car at a lower rate. So you partially pay for your batteries in the car by earning some extra money on helping utility out. And is that a good deal or what? You know, let's look at the gasoline vehicle. 10,000 miles at 25 miles a gallon is going to be 400 gallons of gasoline, maybe at about $1,200. Not right now when gasoline is really, really cheap. But once upon a time, it was $3 a gallon, a mere 5 or 6 months ago. And it's going to release 7,840 pounds of carbon dioxide, which happens to be 3.56 metric tons. There's about 275 million of these creatures on the road right now. And so we're looking at 2.16 trillion pounds of carbon dioxide released by these vehicles. That's, again, with these assumptions. If we have this many million, if they're driving 10,000 miles, maybe they don't drive 10,000 miles in a year. So, but notice that the order of magnitude of 2.16 trillion pounds is right in there very closely to the amount of CO2 released by the transportation sector in a year's time. So, gosh, who wouldn't want to buy an electric car when especially not nearly as many moving parts to have to repair? And guess what? It's not just electric cars. There's electric school buses out there. Florida's using some of the money they got from the settlement with Volkswagen for cheating on their emission on their diesels. And they're buying electric school buses. And then there's electric local transportation buses. And sooner or later, hopefully people are going to be riding on those again. And then there's the delivery truck. Imagine all of those Amazon trucks out there, all those Prime trucks being electric. Sooner or later, it's probably going to happen. Then there's that Tesla pickup down there in the left-hand corner. Pretty fancy-looking vehicle. The only problem with that one is it doesn't make real loud boom sounds when it comes past you and tries to scare you off the road. But otherwise, it's pretty modern-looking pickup truck. And of course, there's electric trains. They've been around for a long time, so we know that we can electrify. These are stuffs that are here. These are commercial products, you know, so we can buy them right now. We can buy the smaller stuff, little scooters and motorcycles and rickshaws and you know, whatever. There's just lots of small 2 or 3 passenger vehicles out there that are being sold various places around the world. So what are the challenges to the grid if we do this? Well, for one thing, we need storage. Just because wind and photovoltaics are less predictable. And pumped hydro has been a long time because we've been using that with nuclear at night. When the nuclear baseload has been producing more electricity than is needed by the grid, they've been pumping water uphill. And that's been going on for the last 50 years. If anybody online here is from the Massachusetts area or in New England, you know that along Highway 2 in northern Massachusetts, there's something like 6 pumped hydro stations along that ridge of mountains there. Battery storage, moving along like crazy. Prices coming way down. Performance, kilowatt hours per kilogram and kilowatt hours per cubic meter, all improving. So the batteries are smaller and more energy dense. Things like flywheel supercapacitors. These things are all at various stages of commercialization. Flywheels are commercially available right now. You can buy a 1 megawatt flywheel. All you need to do is find the manufacturer on the web and order up a couple for your backyard. And if you think of 100 million electric vehicles with 6,000 watt power capacity, that's the level 2 charging, by the way, around 6,000 watts, and able to allow 10 kilowatt hours from each one to the grid, because a purely electric vehicle is probably going to have somewhere between 60 and 100 kilowatt hours of battery storage. So 600 million kilowatts and 1 billion kilowatt hours available just from electric vehicles alone. And that's only with 100 million of them rather than everybody having them. Or maybe it's with everybody having them, but 100 million being plugged in at a time. Another problem with adoption of renewables is if the renewable sources generate more energy than the grid needs, then they're going to try to run into the conventional generators and try to run them backwards. And conventional generators don't like to run backwards at all. So there needs to be some switching in the system to make sure that the power doesn't go in the wrong direction. And that additional power needs to be diverted to storage rather than, or if necessary, even curtailed. At the substation levels, there may be some need to stabilize the voltage amplitude as if neighborhood PV catches on, and a lot of neighborhood PV is there, it's conceivable that electricity would be flowing back into the substation. Normally, when the load on the system increases, they have to change the taps on the transformers in the substations in order to increase the voltage at the source to make sure the voltage doesn't drop below 110 or 112 at the end of the line. And if that has to happen a lot because of clouds going over the sun, then it turns out that if it's their mechanical contacts, they arc when they switch, and they wear out faster. So that we may need to replace those with electronic versions, because power electronics now is perfectly capable of handling huge amounts of electricity power. Consider DC transmission lines where you're running many megawatts down the line, and then you have to convert it to DC and then re-invert it to AC at the other end. And you have to convert it from AC to DC at the sending end. So the amount of power electronics for that is about comparable to, actually much bigger than the kind of contacts that would need to be replaced at the substation levels. Excuse me. Luckily, we're socially distancing this morning, so you don't need to worry about me. So, okay. all this stuff I'm proposing, what does it do to the grid? Well, right now, we've mostly got just power coming out of the generation. It goes on transmission lines to substations. It goes down to a bunch of transformers at the distribution level that feed a bunch of loads. Some of them are bigger, some are smaller, neighborhoods, factories, whatever. That's what's out there today, but when you look at what's going to be out there tomorrow, mark my words, folks, this is what's coming right now. You go to neighborhoods, you're going to have houses that have their own power walls, their own small storage systems. They're going to have their own small PV systems on their roofs. And you're going to have bidirectional power flows at the transformer on the utility pole or at the ground mount, wherever, whether you got underground or overhead distribution. When you get to the factories and the larger loads, the box stores and shopping centers and so forth, then instead of having baby-sized PV, you're going to have smaller PV, but looking in the neighborhood of up to 50 kW, 100 kW. That's still small compared to utility scale. At the substation, everything gets scaled up. Bigger size storage, bigger size renewables dumping in at the substation level. And then the important thing here is the connection between generation and substation. You need a bidirectional link there to make sure that the power only comes out of that generator and does not go from the substation back to the generator. And that's what the bidirectional link, it has to sense that power is coming back out of the substation and it dumps it into the big storage if necessary. If the generation is not meeting the full needs of the substation, then it can take some power out of the big storage and send it down. So look for this happening over the next 10 to 15 years. It's imminent. It's going to happen. All right, I'm going to take a look here and see if there are any questions. Let's see, Q&A. I see we've got 27 folks out there. Here we go. How do you factor in the carbon dioxide generated by the manufacture and installation of the renewable energy? Well, John, that's a really good question. And in general, it's not factored in because no matter what you're going to manufacture, there's going to be some carbon dioxide generated. Now, in the perfect world, as we make industry more efficient, there's going to be less and less and less carbon dioxide generated in the process of making renewable energy equipment. One thing that's important to pay attention to here is the energy return on investment from renewables. And what does that mean? That means how many kilowatt hours can you get back for every kilowatt hour that you invest in manufacturing some photovoltaics? And the answer right now is something like 20 to 1, and it's getting bigger. So for every kilowatt hour that you spend making the equipment will give you back about 20. So what that effectively means is that you could be generating renewable energy equipment with renewable energy, and effectively then 80% or so of the your energy overhead on that would be about maybe 20%. 20%? No. Is that what I mean? If you get a 20 to 1, no, that's 5%, isn't it? I'm not thinking clearly here. So in any case, we're headed in a direction so that less energy will be used in manufacturing renewable equipment. And of course, you have to talk about the mining and all that kind of stuff. And so that, but you know what? It all comes out in the cost. It all comes out in the cost of the equipment because every dollar has a BTU component to it. So that if you make the stuff cheaper, one reason photovoltaic cells are now so a whole lot cheaper is because they have come up with a process for refining silicon that uses a whole lot less energy than it used to take 25 years ago. So these are the things that are happening. That's why we have scientists out there. They figure this stuff out for us. And every once in a while, somebody actually believes them and actually does what they suggest. Okay, let's look at Henry Simpson here. What kind of electric hybrid car do we own? We own a Honda Clarity. We love it. We got up at 6:30 this morning and drove it to the store, loaded up with groceries so we don't have to leave the house again for another week or two, and didn't burn any fuel, any fossil fuel at all from the tank in the car. It used up maybe, let's see, that was about a 15-mile round trip. So it used maybe somewhere around 4 kilowatt hours or something like that. Let's see, and David, 1141, where will all the additional power generation come from if all the cars are EV? Well, it would create a very large increase in the total demand of the U.S. grid. Yes, that's absolutely correct. And that means that, but we know exactly how much that would be. And there's going to be several things that happen. We're going to be, I say that we have the opportunity to, first of all, cut down significantly. If we have a lot of zero energy buildings out there, then that energy that would have gone to the buildings can go to fueling electric vehicles. And in fact, in the discussion yesterday on this zero energy building, the folks who are designing these are starting to incorporate additional source energy on the site in order to charge the electric vehicles. So you make a good point. And of course, the utilities love it because it means they're going to be putting in a whole lot more cars. So what the bottom line here on this answer, David, is that, and again, this is in a perfect world if we do the things right, it means that we're going to steal some of the power that would be used from in inefficient industrial processes and inefficient dwelling unit processes and shift that over to the use in electric vehicles instead. And yes, it's going to take more electricity to fire up the EVs. And, you know, we're talking about doing things business as usual. And EVs with 3.5 miles per kilowatt hour. And I can tell you, we did a lot of work on solar golf cart a while back, 15 years ago. And the golf cart was getting 8 miles per kilowatt hour on its lead acid battery. So smaller, more sensible local transportation will make a difference as well. So let's see, where will all the additional, okay, here's another one. Are there incentives available from federal New York State to install solar panels? I think the federal 30% tax credit is still there. New York State, I think, has, I'm not sure. I know that New York State has had a significant, out on Long Island, you see a lot of these little BMW i3s, electric vehicles, because they had a utility was giving huge rebates to people for buying those electric vehicles. And also up until a certain number of vehicles are sold, on ours, we got a $7,500 right off the top of our income tax to help pay for the car. So you need to look for the incentives. I think New York State has them, but I'm not familiar for sure. We'll have to see. So let's see if I miss anything here. Open to, answered, just, I'm not sure what that means. I think we're okay. Let's move on. I'm going to close this out for a minute. And thank you for the questions, by the way. Let's see, we've got 13 minutes to go, and that should be just about right, because now we get to talk about government leadership, something that I'm not allowed to give my own personal opinions. So, but let's put it this way. Here are some government leadership opportunities in order to implement the plan that we've just proposed. greening up the government buildings. Okay? Greening up the government transportation. Good grief. Look at all the fleets. I mean, the military is already trying to green themselves up as much as possible because they understand how that is to their advantage. Can you imagine hauling fuel to the front lines? I saw some numbers on that, something like $100 a gallon, maybe more. I don't know exactly, but it's extremely expensive hauling fuel to the front line. It's a whole lot cheaper to haul photovoltaic portable systems to the front lines to power up whatever. Greener incentives for green economy, such as a carbon tax. Yeah, we're going to see that, I think. If we don't, it's crazy because it really should be. Because if somebody wants to drive a gas hog, okay, just use that money, collect an extra 10 cents a gallon for the gasoline and use that for rebates for people who go electric. It's been going on with carbon cap and trade for about 20 years now. So this isn't new. We just need to extend it a little bit. Charging electrical vehicles at government buildings. We're doing that here in West Palm Beach. I'm guessing that other areas are doing that as well. I can park my car at a library in town and plug it in. There's only the capability for charging 2 electric vehicles, but well, you got to start somewhere. Green military, already mentioned. Green planning and development. And here's where we come in, folks. We are the design professionals, and we need to think about green planning and development. Maybe a nice little electric train that goes up and down on this golf course community, which has been built over a golf course when nobody's playing golf anymore. We've got a lot of empty golf courses down in our neighborhood here now, and they're probably going to build houses on them. So I sure hope they plan that nice and green. One of the problems with this is that commercial investments, they like paybacks in a year. And some of the paybacks here are 4-6 years out, something like that. And but there could be an incentive, government incentive, tax incentive, whatever, so that industry would see fit to get greener. And knowing now that it's possible to build a zero energy building and you actually save money over the life of the building, why are we not going directly to zero energy building codes? We need to be pushing for that and building accordingly. We can do that. And even incentives for zero energy renovations and conversions. How about a little extra rebate if I put in we can't do solar in our building, but I can sure put in a water heating heat pump and a super efficient air conditioner when I have to replace them. We already did that with the air conditioner. When our water heater goes down, it's going to be replaced with a water heating heat pump, no question about it. So yeah, there's a lot of stuff that can come in on the incentive category. All we need to do is elect people who realize how important it is to do that. People who have some awareness of those 11 tipping points that we talked about at the beginning. The other interesting thing here is, where does our money go? People are going to start reevaluating where their money goes. I've let my broker know that I don't want any of my money in fossil fuels. And the only place I might have some money in fossil fuels now is if it's in a mutual fund that has some small amount. But anyway, here's the big guys who lend to fossil fuel. They're probably making a mistake. I mean, we're seeing right now what's happening in gasoline. People aren't using it because of the pandemic. But as people start going electric, gas is going to go out of style. So maybe we don't need those pipelines. We wouldn't if we follow the plan proposed here. And if we don't do these things, that CO2 level is going to go up to the point where it goes out of control. And I don't want that for my grandchildren. I don't think any of you do either. In fact, I've got a great grandchild now on the way to do it at the end of July. And I would like that young man to end up with a much nicer world. So here's another slide. It's a picture of effects on gross domestic product. And we're looking at the Paris Agreement conditions, which are very close to what the Green New Deal is, by the way. So whether we call it Green New Deal or Paris Agreement, anything in green is the effect on the gross domestic product if we go with efficiency, super efficiency. And if we don't, if we go business as usual, then it goes red. Notice that the United States is going to lose a whole lot bigger percentage in per capita GDP. And by the way, the numbers in the green box on the left-hand side there are not correct. I interpreted the vertical scale incorrectly when I made this slide, and I only caught it this morning, and I didn't have time to fix it. But the point is still there, that look what happens to the Chinese. They're already going efficient. And they're going to come out smelling like a rose. Look at the European Union by going efficient. They're not losing any percent per capita GDP because they've been investing in renewables for years and years. The German and the number of the countries in Europe that have had these feed-in tariffs, and even Russia, look what happens for them. If they go efficient, they all get ahead of us because we've been a little bit too reckless with the way we've been throwing away energy, but the only thing we can do to prevent it from getting a whole lot more serious is to not to do anything. So when people ask about what's out there and what do we have to do, clearly this is, we have to go with the equivalent of the Paris, excuse me, the Paris Agreement or the Green New Deal. Who's affected the most? Boy, agriculture is really getting a beating. Floods like crazy. Just last year alone, more than $2 billion lost in Iowa and Nebraska, just due to floods. You know, I think due to global climate change. Well, it's the first time they've ever had it that bad. So it sure looks like it's a change in the climate, different from normal. Infrastructure, wow. You know, housing, airports on coast. Imagine up in New York City, flying into JFK over the water. How long is it going to be before JFK is gone? Docks, railways, interstate highways, all kinds of stuff. Even water-resistant fiber optic cable is not waterproof fiber optic cable. It's just resistant. So groundwater levels get up and start getting in the joints and connections in the cable. Could be a problem. So not a good thing for folks. Now, what about greener ethics? Okay, well, saving the planet has to be a part of our codes of ethics in all of the different engineering. And I have to say, I haven't seen all the codes, but I know the civils have included that now in the ASCE. We've just shown that carbon dioxide reduction can be profitable and cost-effective for everybody. It's a win-win deal for everybody. Millions of new jobs out there. And the design professionals, our job, because we understand the math, we need to convince our clients that, hey, this is the way you really need to go. Don't even think about another way. You're not going to be able to afford it. It's like building, you know, we've got wind load, very strict wind load requirements. We have to design to 170 mile an hour winds now in Florida. Nobody fusses about that. They just do it because they know what the results can be if you don't. We've seen it. The problem with these other results is they're not quite as obvious. So we have to understand it. Yeah, they may not be obvious, but they're there. So we need to get involved in this, and we got to do it now. And this is the last slide, folks. So the bottom line here is that, well, one of my favorite sayings that I once had was that when all is said and done, a lot more is said than done, and we can't do that anymore. We got to get there and do it. And we're not just doing this for our children and grandchildren. There's a lot of other creatures on this planet that are living things that are depending on us, and we depend on them. So it's time to act. So let's go back to the comments now again. Let me find that. Here's Q&A. What do we got? Okay, no questions open, but type away, folks, if you have any questions. We've got about 5 minutes. We can discuss questions. I saw something flash up here. Oh, chat. Okay. Let's see what we got here. Oh, okay. Here's a note. Be sure to read this. Find the box that says chat and read this note from Hisham at PDH. Thanks for attending. We managed to get through it right in about the right amount of time. It is 11:59, folks. I hope it was worth your time this morning, and hope you learned something. I hope you'll be able to go out there and get busy with it. Don't forget to take the quiz. Webinar slides on the webinar page. No charge, just download them. They're all yours. If you want any of the numbers, calculations to show your friends, download the presentation and show it to your friends. Circulate it. It's not there to just gather dust by any means. Fill out the review. We appreciate your comments. Very much appreciate the comments. We send them in. We try to do quality control here and get things done as best as possible. Okay, so there's a note from, okay, is there any, okay, any incentive available from feds or New York State? And, oh, how much does it cost to install 451 square meters of roof panels? Good question. Okay, let's see. Square meter roof. That's about 200 watts worth, and so that's okay. About 9,000 watts, and at about $3 a watt. So that's about $27,000, something like that. Let me make sure that I got that right. Number for you to use. Check this calculation again after we're done here. So I may have run through it too quickly. Oh, let me get my calculator out. Let me just run it. 451 square meters. That sounds familiar. That must be the roof we had in the example. Times 200 watts per square meter is 9,020 watts. Wait, is that right? All right, I'm sorry, 451 times 200. Yeah, okay, if that, in fact, if that's, oh, 451 square meters, that is a fairly big area, isn't it? Yeah, in terms of square feet, that's way over 1,200, almost 1,500 square feet. All right, 90,200 watts, maybe that would be at about $3 a watt. So yeah, times Yeah, about $27,000. Then you have to figure out your payback on it. And again, you can, this can all be done using that SAM simulation program, but if you just use 1,500 kilowatt hours per year per kilowatt, and then multiply that out by the cost per kilowatt, it'll give you a payback period on that. It may seem kind of high at 27,000, but that's a lot of PV. So actually payback on that's probably about 6 years. Okay, what else we got here? One new message here down the bottom. Okay, from James. Thank you, you're welcome. And let's go back here to Q's and A's and see if there are any more of those. Appreciate your being willing to type in the questions. Having open microphones with 28 people in the webinar. You've probably all been on webinars similar lately because a lot of things going on. Fuel utilization efficiency is about 35%. Yeah, right. Using fossil fuel generated power is better than directly burning gasoline in conventional gas auto. Yeah, we just did that. The analysis we did, the 2.2 pounds of coal, that's actual coal per kilowatt hour. Not 2.2 pounds of coal, but 2.2 pounds of carbon dioxide per kilowatt hour generated by coal. And that takes in the coal conversion efficiency, okay? So the analysis we did already takes that into account. About 0.88 pounds per kilowatt hour for natural gas and about 2.2 pounds per kilowatt hour for coal used in generating electricity. So there's no question. I think we showed that it would take about, what was it, 70 or 80 miles per gallon with the direct gasoline burning to compare with an electric vehicle powered by electricity generated by methane. So yeah, you need to get almost, and so you buy a hybrid. And a hybrid, some of them are getting around 60 miles to the gallon, so that's coming close. But even the hybrid doesn't quite make it to the equivalent efficiency of an electric. So I hope that answers the question. Yeah, and I appreciate that one. That's a good thought. Okay, so let's see what else. I guess that's it for questions. And let's just see if there's any more chats. And okay, well, the question is, where's the quiz? The quiz, go to the website. And any questions, go to the PDH website. And I'm not exactly sure, but if you go to the website or on the PDH website, there's a phone number. You can call the boss. He's very receptive to calls if there's anything you don't find on the website. But you should be able to download the quiz from the website and fill it out, and I think you just email it back in. I haven't taken it. Well, I did take it, yeah, because I had to come up with the answers. All right, well, thanks, everybody. I'm going to take a look at the number of participants. We're down to 25 now, so I'm going to stay signed in until everybody has signed out. To sign out, you go up to the what's on the top of my screen under More, which under More is the chat room, but at the very bottom of that pull-down menu under More is Leave Meeting, or hit the alternate key and a Q, and that'll get you out of the meeting. But if you have any other questions, type them out. And Otherwise, thank you all for participating. We appreciate it. We hope it's been worth your while.